And I'm in a group with Hope and Ralph, and we're going to show you how to find the area enclosed by an ellipse. So this is an ellipse, and we're going to find the area of it. And this is the equation of an ellipse. Right? So first what we're going to do is we're going to solve for y of the equation. So I'm going to minus x squared over a squared. I'm going to get y squared over b squared equals 1 minus x squared over a squared. Then I'm going to multiply it by b squared, and this is what we're going to get. And then I'm going to take the square root to get rid of the y squared. And I'm also going to find the common denominator for this expression. And this is what we get. Then I'm going to factor out a squared under the square root. And then I'm going to bring out b squared over a squared out of the square root. And we're going to end up with y equals plus or minus b over a times the square root of a squared minus x squared. And since in the area of an ellipse can't be negative, we go ahead and get rid of that and deal with the positive. Right, so this is our equation, y equals b over a times the square root of a squared minus x squared. Right, and then we're going to find the area for it. And because the ellipse is symmetric with respect to both axes, the total area is a times a equals 4 times b over a times the integral from 0 to a of square root of a squared minus x squared. And now I'm going to pass it off to Hope. She's going to show you some more.
Okay, looking at where Tyler left off, you can see that the inside of the integral is already, it already has the expression so that we can use the trig substitution x equals a sine theta. The derivative of that is a cosine theta. We can also rearrange this expression right here to get that theta equals the inverse sine of x over a. Since we're using substitution as well, we're also going to have our new limits. So from 0 to a, it's going to become, we're going to use the theta and plug these in as our x values. So it's going to be inverse sine of a over a, which is inverse sine of 1, and inverse sine of 0. And that comes out to pi over 2 and 0. Those are our new limits. So now we're just going to rearrange this expression with the substitution and our new limits. So we get 4b over a from the integral of 0 to pi over 2, square root of a squared minus, and our new x value, which is a sine theta squared times, and this turns into a cosine theta. As you can see, that's what our derivative, the dx equals. You can simplify this further to get 4b over a from 0 to pi over 2 of square root of a squared minus a squared sine squared theta square root times a cosine theta. You can also simplify this further by taking out factoring out the a, and we'll get 4b over a from 0 to pi over 2 times a squared square root of 1 minus sine squared times cosine theta. You can simplify this using the Pythagorean identity. 1 minus sine squared equals cosine squared. So this part is going to be cosine squared. The square root of cosine squared is cosine theta. So we get 4b over a from integral of 0 to pi over 2 times a squared times cosine squared theta. I can explain further.
Oh, I fucked it up. Just press the red button.
Which?
Okay, so from here, a squared, we can factor that out, and then we'll get 4ab cosine squared theta. And then from here, we can use the half angle identity, 1/2 times 1 plus cosine 2 theta. And then from there, we can factor the 1/2 on the outside of the integral, and then that'll give us 2ab. And then if we take the antiderivative of 1, it's going to give us theta. Antiderivative of cosine 2 theta is going to give us 1/2 sine 2 theta. And then we plug in pi over 2 and subtract it by plugging in 0. And so that gives us 2ab pi over 2 plus 0 minus 0, which is pi times a and b.